Sullivan from Western University, who will be talking about cognitive ontologies, epistemic communities, and coordinated pluralism. And on Friday next week, November 6th at 3:30 p.m. Eastern Time, Liz Westerlund from Pitt, the Department of Economics at Pitt, will be giving the fourth lecture in the annual lecture series at 3:30, I said, on the topic of gender differences in task allocations, competition, and volunteering. So that's it for next week. Let me remind you, we're using Zoom webinar, and that means that you are attendee. If you have a question for our speaker today, please go to the bottom of your screen, click on Q&A and write your name. During the Q&A session, I'll promote you to the status of panelist, and you will be able to talk to Mike directly. I believe that's about it for the event. I'll remind you about how to proceed. Today, it's my great pleasure to introduce Mike Schneider, who got his PhD this year in 2020. He spent at Irvine in the Department of Logic and Philosophy of Science. His advisor was our friend Jim Weatherall, with an all-star committee. I just double-checked Jeff Barrett, Menchak, and Kyle Stanford, really, friends of the center at Pitt. So Mike has been the postdoctoral fellow at Pitt, at the Center for Philosophy of Science at Pitt, since the beginning of the year. It's been a wonderful addition to the life of the center. He specializes in history and philosophy of physics, but also social epistemology of science and the general philosophy of science, with interest in values and science, for example. He's published widely on all of these topics in the best journals in the field, as one usually says. Philosophy of Science, BGPS, actually twice in Philosophy of Science, BGPS studies, and he's given really many different talks. He also won some awards, including the Rob Clifton Memorial Book Prize for What's the Problem with a Cosmological Constant in 2017. Today, Mike is going to be talking about Srtabs in the dark sector. We've had a lot of very good titles this semester for talks, but this one is really also really quite nice. So Mike, the floor is yours, and I'll be back in 1 hour.
All right, thank you for that warm introduction. I'm just going to hide my face from myself here. Okay, so this project has evolved a lot over the past year. So this is the third time that I've given a talk with this title. And each time I've presented something different, or at least emphasized a different part of how I'm thinking about the whole subject. So maybe, this is all to say, what I'm going to talk about today is just one stab in the dark sector. But I'm excited to hear reactions about it. So this is where I want to begin this talk. This is just a fantastic picture. It is a highly stylized, unapologetically theory-laden and perspective-laden visualization of what I think philosophers often mean by the world, or maybe I should say the whole world, or going in the exact opposite direction, all that we may presently observe, but with a pretty serious slant toward what astrophysicists and cosmologists think is most worth their dwelling on. So to be a bit more exact, this is an artist's rendition of the observable universe according to our current best physics today. It's inspired by a logarithmic scale reasoning about what astronomical objects are encountered as an observer looks farther and farther out in every spatial direction. Except in an act of maybe dogma, or what I like to imagine is a conscientious nod to the artist's memory of grade school science. The artist has chosen with all of their freedom to place the center of the observable universe with our sun, with the Earth orbiting it. So the observer here is a star. In any case, the idea here is that because the speed of light is finite in units of velocity that are suitable for tracking motion of astrophysical bodies through space and over cosmic time, as we look out into the farthest reaches of space, we are, in a certain respect, just abjectly failing to do so. We are in equal measure looking back in cosmic time. So, roughly speaking, in this picture, concentric circles radiating out from the sun at the origin mark out our observable universe in sequential moments farther and farther back in cosmic history. The very thin red ring nearly at the edge of this picture marks the moment of recombination, beyond which the observable universe, at the earliest fleeting moments in cosmic history, is electromagnetically opaque. And don't worry about the gray-black border beyond the thin red ring. That's either going to be the Big Bang singularity, or else maybe the Planck regime. That's a conversation for another time. In fact, what I'm interested in, at least today, is late-stage cosmology, which is in contrast with early universe cosmology beyond that thin red ring. Late-stage cosmology spells out what's happening in our observable universe in the present day at the largest accessible scales. So in this picture, this is all that's contained within the thin red ring, but considered at large enough distance scales that it doesn't really make sense to talk about the individual structures of planets and stars, all that stuff in the center. So in other words, my talk today begins and ends with the red-orange iris in this picture. So this depicts the part of the world that we often call the evolution of large-scale cosmic structure. Now, recall that, as I said, cosmic time clicks forward as you move inward toward the sun in this picture. So what you can see in the iris is starting from a homogeneous bath, we get the emergence of these long filaments separated by great voids. So our understanding of this part of the world, again, the evolution of large-scale cosmic structure, it comes from our embrace of lambda CDM, a cosmological theory that I'm going to have more to say about as I go on. So my goal in this project that I'm talking about today is to draw attention to a curious state of affairs concerning empirical claims about the evolution of large-scale cosmic structure, as they show up, as these claims show up in dark sector research, hence the title, Stabs in the Dark Sector. Now, this is something to do with developing future fundamental theory in physics. And in fact, I think the curious state of affairs is revealing of a more general thesis about theory development in fundamental physics, which I'm going to have lots to say about in a moment. But for now, I just want to give you an impression of what amounts to dark sector research and what does the evolution of large-scale cosmic structure have to do with it. So here are going to be a few examples of dark sector research. And my goal is not to rehearse them in any great detail. I just want to give you all something to chew on as we go through this talk. So first example, dark energy is typically understood as what should give rise to the slowed growth rate of what you might call non-trivial large-scale cosmic structure within our present-day universe. So you can think of this as how quickly those filaments and voids in the picture come to be or materialize out of the homogeneous bath. That slowed growth rate is an expected effect of dark energy. So long as dark energy fuels the accelerating rate of expansion of our large-scale spatial universe, what we might call trivial large-scale cosmic structure, as according to the theory lambda CDM. But it has recently been conjectured, a couple of years ago now, that many models of dark energy that are understood to do this, they could turn out to be prohibited in fundamental physics, given the tools that are provided by string theory. So as a consequence of this, a sustained commitment to those tools from string theory in the course of developing future fundamental theory, that commitment might compel us to revise our understanding about how dark energy ultimately does what it's supposed to do. So that's one example specifically concerning dark energy within the development of future fundamental theory, and specifically concerning an open conjecture about the string theoretic toolkit that some might wish to use to develop the future theory. Here's another example. Cold dark matter is typically understood as what should give rise to the characteristic lumpiness of the same non-trivial large-scale cosmic structure. So you can think in the picture, the pattern, roughly speaking, that's exhibited by those filaments and voids. Now, this is an expected effect of cold dark matter, this lumpiness, so long as the phenomenology of cold dark matter approximates at scales relevant to lambda CDM the gravitational dynamics of an homogeneous perturbed pressureless fluid. And such an effect at cosmological scales is often attributed to an as yet unspecified particle account of cold dark matter within future fundamental theory. Now, this account is also thought to simultaneously give rise at galactic scales to a dark particle phenomenology in the presence of known environmental factors. So, for instance, active galactic nuclei, supernova, winds, and so on. This multi-scale phenomenology, given those environmental factors, thereby informs an extension to the standard model of particle physics, as should fall out of the future fundamental theory. So this is an example specifically concerning cold dark matter within the development of future fundamental theory, and specifically assuming that a certain kind of dark particle phenomenology is relevant to the same subject matter when it is considered at galactic scales. And I should mention that Michaela Massimi discusses some interesting issues in this example, as well as with the next example after a fashion, in her 2018 paper on multi-scale modeling in cosmology. I've just bulldozed over the subtleties involved in the multi-scale modeling logic that gets employed in these examples. But here's the next example. The multi-scale phenomenology that is otherwise thought to be captured as the combined effects of dark energy and cold dark matter in the presence of environmental factors. It has in some other projects been taken to motivate what you might call a conjoined understanding of both effects within the context of future fundamental theory. So I have in mind here the case of emergent or entropic gravity, where there's some fundamental physics responsible for letting us talk about space-time points or regions growing entangled with each other. Final example that I'm going to give, somewhat similar to the previous example. The combined effects at cosmological scales have in some other cases, been taken to motivate an alternative classical gravity theory, which the future fundamental theory is ultimately meant to recover in a suitable limit instead of general relativity. Now, these alternative theories, for instance, mimetic gravity is one, they usually have extra degrees of freedom compared to general relativity when we construe both it and general relativity as a modeling exercise. Now, as models, those extra degrees then get tuned based on all of the same multi-scale considerations as in the previous example. So that was a lot of physics. This slide is now very busy for my personal aesthetic preferences. Note how getting clear about any of these examples would seem to require a lot more. And in particular, it would seem to require a host of controversial assumptions about future fundamental theory. And it may turn out that some of those assumptions are, perhaps upon close inspection, pairwise mutually contradictory, so that entertaining some of the examples could turn out to come at a cost of precluding the intelligibility of others. Now, if we construe these examples as competing proposals for further research in the dark sector, we might conclude that the different examples take for granted different base conceptions of what the future theory will be like. Conversely, embracing any one proposal seems to be tantamount to stipulating that future fundamental theory will indeed wind up featuring the right sort of infrastructure in order to warrant, in retrospect, our having embraced the proposal in the first place. This sort of messiness is standard fare for any discussion that would involve jumping into the trenches of ongoing theoretical research. For instance, to compare the respective theoretical virtues of the different examples construed as competing proposals. I take Karen Crowther to be someone seriously engaged in that sort of project, diving into how we should make sense of what we want to think of as the domain of quantum gravity, but as we can talk about it today, not yet having achieved a satisfying theory of quantum gravity. So she tries to do this by leaning on the common thought that there are various principles of quantum gravity research, and then cashing out these principles as we currently can make sense of them, talking about their merits, their demerits, and so on. Conceivably, this could give her resources to cross-compare research proposals that are situated in the context of quantum gravity still in development. That's not what I'm going to do here. Instead, just having peered in from the edge into the messiness, I think there's something puzzling about the state of affairs in dark sector research, as witnessed across all of the examples. And that is what I'd like to focus on. So first, I'll say the bit that I don't take to be puzzling. What the examples illustrate, I think, is a sense in which claims in dark sector research about the evolution of large-scale cosmic structure, these claims wind up constraining the development of future fundamental theory in physics. But now the puzzling bit, as I see it. Those claims about the evolution of large-scale cosmic structure, they come from our embrace of lambda CDM, which I haven't actually said that much about. But lambda CDM came to be, in the first place, as a cosmological scale application of our current fundamental theories in physics. Now, our current fundamental theories are precisely what future fundamental theory in physics is intended to replace. And in fact, it's intended to eventually pave the way for a future theory of quantum cosmology as well. So all told, dark sector research seems to provide a means by which our current fundamental theories are leveraged to help shape their own replacement, as well as to ultimately do away with the relevance of the very application which has permitted them to be leveraged in this way. Stepping back then, I want to get a better sense of the instrumental role that claims about the evolution of large-scale cosmic structure get to play within dark sector research, such as might make sense of this, to me, puzzling, seemingly self-undermining situation. And ultimately, what I want to argue is that it's a mistake to regard these claims as empirically constraining future fundamental theory via constraining the physics of the dark sector, which is expected to feature within that future theory. Instead, what the examples illustrate to me, I think, is a sense in which these claims amount to empirical constraints on theory development itself. That is to say, our present commitments to those claims constrain our present activities, which are directed toward the achievement of a future theory down the road. And the upshot of this view is that close consideration of how this works in the case of dark sector research can enrich our understanding of how future fundamental theory will come to be, or really how it will be brought about in light of where we have come to be in our understanding of the world today. So, as just stated, my goal is to advance a local thesis concerning the continuity of scientific knowledge across theory change, specifically in regards to contemporary fundamental physics. And as I've just suggested, dark sector research provides a probing case study on this point. Nonetheless, it's famously difficult to articulate any thesis on the continuity of scientific knowledge at all. And I take this difficulty very seriously. So the first part of my talk will be dedicated to getting at least some grip on the subject of continuity. And I'm going to borrow from an account of evidence that's developed somewhat recently by Nora Boyd, formerly a graduate student at Pitt, in order to distinguish between a notion of expected empirical constraints on future theory and a notion of empirical constraints on theory development itself, which is directed toward achieving that future theory. Then I'm going to introduce a standard view of dark sector research, which lines up with the notion of expected empirical constraints. I'm going to argue against the viability of that view, which will lead me to favor an alternative presentation, which lines up with the notion of empirical constraints on theory development. And this alternative actually builds on some previous work of mine. So this project connects up some past threads about the activity of theory development with the new topic for me of empirical constraints. And so that's exciting for me, probably more than for any of you. Finally, I'm going to conclude with just a bit about the stance taken toward lambda CDM in this alternative presentation, as contrasted with a more familiar gloss on the subject. So lots to do. Let's dive in. In a 2018 article, Nora Boyd provides a new means by which our current theory-laden empirical claims may be taken to persist across theory change and to thereby participate in future scientific endeavors. Her central insight is that the epistemic utility of our current theory-laden empirical claims derives from their provenance. Roughly speaking, this is the means by which those claims came to be as empirical evidence within a given research context. So enriched lines of evidence, theory-laden empirical claims that are suitably enriched to include considerations about their provenance. These wind up as adaptable things, which can be appropriated to constrain theorizing in contexts other than those relevant to the moments of their birthing. So as one particular instance of this adaptability, enriched lines of evidence may be understood to constrain a future theory, which it just so happens is not yet developed. Notably, from this perspective that's adopted in the article, that case is no more or less extraordinary than the same sort of evidence being understood to constrain a current theory, which just so happens to reign over a numerically distinct domain. So in particular, we have what I think is a nice quote. Thus, one can think of enriched lines of evidence as including the rich, perhaps bottomless reservoirs of background information implicated in the production of an empirical constraint. Different circumstances will call for interrogating this reservoir to various extents. Boyd's account of enriched lines of evidence can thereby moonlight, for my purposes, as an account of expected empirical constraints on future fundamental theory in physics. So the idea is to render our current theory-laden empirical claims as expected empirical constraints on future fundamental theory. One needs only to expect to enrich them upon the achievement of that future theory in the sense intended by Boyd. This is an expectation precisely because it is difficult to spell out in advance of the future theory itself what determines that an enriched line of evidence is, in her terms, well adapted to that future context. In other words, in the case of future theory, the relevant circumstances that were mentioned in the quotation on the previous slide, they're currently ill-specified, and they will remain ill-specified until such time as the future theory has come to be developed. But now, it's another consequence of the adaptability of Boyd's enriched lines of evidence that will wind up essential in my considering dark sector research. Namely, enriched lines of evidence may be pertinent to theorists' decision-making in the course of theory change, where theories are expected to presently shift and our attitudes toward them are expected to evolve as a direct consequence of the theorist's professional activity. And this, I take it, is precisely the situation in which theoretical physicists as a community or profession find themselves. They are in active pursuit of a future fundamental theory, which accomplishes a variety of present aims. Those aims circumscribe the future domain of quantum gravity as we understand the subject, perhaps pluralistically today. As a consequence, we can use Boyd's account of enriched lines of evidence to bootstrap an account of empirical constraints on theory development in fundamental physics. These are constraints on that decisions-laden activity, which is intended to culminate in our achieving a future theory of quantum gravity. So the thought here is that our current theory-laden empirical claims, rendered as empirical constraints on theory development, they may shape the way theoretical physicists come to achieve the future theory. And notably, this is separate from the way the same sorts of claims, rendered as expected empirical constraints on the future fundamental theory, ultimately enable the world to push back against that future theory. So one might be inclined, many of you, in fact, might be inclined to deflate the further notion of empirical constraints on theory development by means of reducing any instance of such a constraint to a constraint of the first kind, an expected empirical constraint on the future theory yet developed. So in particular, theorists may look forward to our current empirical claims being rendered as empirical constraints on the future theory that they intend to develop. And this thought goes, they may thereby use that expectation about tomorrow's constraints in the meantime to influence their decisions today. Now, I would like to resist this inclination, and I'm happy to say more about why in the Q&A. For now, I hope you'll just grant me that the two are plausibly distinct notions. The first captures the sense in which fundamental physics research may be regarded as a proper empirical subject like any other scientific endeavor. The second, meanwhile, has to do with the process of theoretical research. And in particular, how that process implicates the world around us as we presently understand it within the eventual contents of the future theory. So that hopefully clarifies some of what I meant early on when I suggested that we're going to wind up understanding claims about the evolution of large-scale cosmic structure to constrain theory development in fundamental physics via dark sector research. I mean to claim that dark sector research in this talk is ultimately going to have to do with empirical constraints on theory development rather than expected empirical constraints on the future theory. Now I'm going to want to talk about the other part of that claim. What is dark sector research? So according to one standard presentation of dark sector research, dark energy and cold dark matter are two poorly understood features of our current understanding of fundamental physics. Nonetheless, the belief that there are such things, fundamentally speaking, as dark energy and cold dark matter, this commits us to the descriptive accuracy of certain predicted effects, which are so subtle as to only be noticed by our current means over immensely large scales. Now, lambda CDM, a current theory that is deployed at those immensely large scales, thus provides one means to infer the presence of such things. Dark sector research on this view then furnishes us with speculations about further details concerning these targets within the domain of current fundamental physics. Meanwhile, we expect that the features of each of these respective targets, so dark energy and cold dark matter, we expect that they'll be preserved, at least to some degree, in the course of developing future theory. So any details about them that are explicated today get to stand as clues about what will eventually be a part of the codified future fundamental theory. So dark sector research on the whole is understood to furnish us with these clues. And these are really expected empirical constraints on the dark sector as we presently expect it to show up to some degree within the future theory. And I wanted to flag a recent article by Siska de Verdemacher, also recently out of Pitt, which dives into the idea of dark energy and cold dark matter amounting to targets in the context of at least some experimental work. I think there are some interesting connections between my current project on the theory side of dark sector research and hers, which is more about the experimental side. So I'd be happy to talk a bit about that in the Q&A as well. So the trouble with the standard presentation is that although standard, it does a disservice to our understanding of dark sector research. This is because a belief that features of our current theoretical understanding will likely be preserved doesn't, at the end of the day, ground our leveraging the fact of its preservation or even our leveraging the fact of its likely preservation. In other words, the role that targets like dark energy and cold dark matter play within expected empirical constraints on the future theory, that doesn't itself justify that those features be built into the future theory or put into the future theory during its development by hand. Now, I don't have the time here to give the exact argument for this claim, but as a consequence of the claim, clues about the dark sector, construed as expected empirical constraints on the future fundamental theory, these cannot constitute grounds to include dark energy and cold dark matter in developing the future theory. In other words, the presentation of dark sector research that I've rehearsed so far, the standard presentation, it occludes what I at least here care about most. Namely, it occludes how empirical claims about the evolution of large-scale cosmic structure are rendered as empirical constraints on dark energy and cold dark matter, sure. But importantly, it does so in the shaping of the future fundamental theory in the first place. In other words, I think my focus here ultimately demands a different presentation of the subject of dark sector research. And fortunately, I'm here to tell you that there is another presentation. We can instead regard dark energy and cold dark matter as features that we impose on future fundamental theory. It's a demand in the course of our developing it. On this perspective, the two are features that we presently expect to be introduced into our corpus of knowledge only upon the achievement of the future theory. Consequent to that achievement, empirical claims made today about the evolution of large-scale cosmic structure may be rendered in retrospect descriptively accurate by the lights of the new theory. So this alternative builds on some previous work of mine, so I apologize for the self-promotion. In that previous work, I consider the role and status of the cosmological constant problem within quantum gravity research. In the case of the cosmological constant problem, whose details aren't going to be important here, various semi-classical assumptions about the future theory of quantum gravity give rise to some or other problem that needs to be solved. But outside of the context of quantum gravity research, where there aren't any semi-classical assumptions, there just is no problem. The upshot is that work aimed at solving the cosmological constant problem may be regarded as well-motivated, specifically within the context of quantum gravity research. And meanwhile, that work simultaneously provides means by which the future theory of quantum gravity comes to be developed. And this is because to even articulate or formulate the problem precisely takes for granted or requires articulating new theoretical infrastructure to do so. But then having formulated the problem precisely, there is now a perfectly ordinary, outstanding empirical problem to solve within that newly articulated theory. So now, in a follow-up article, I defend the epistemology behind this method on the basis of what I call anticipations about the future theory. And let me try to sketch the idea because it's going to turn out to be important for understanding what I mean by treating dark energy and cold dark matter as demands or impositions on the future theory. So first, note that future physics is not the world. Without meaning to be too metaphysically loaded, the world simply is, at least that's how we often talk about it. Future physics, meanwhile, is something we bring about. So what does this distinction amount to? Well, time and again, we are surprised by how the world has turned out to be. Time and again, we find that so far, we have been mischaracterizing or misunderstanding what seems now, in retrospect, to maybe matter most. Now, in a sense, so too have we been surprised before by how future physics has turned out to be. Just so, if we have also been surprised about the world, which our future physics is supposed to say something about. But future physics, because of its relationship to us, inevitably has a lot to do with where physics has come so far. This is not so of the world, whose only relationship with where physics has come so far is something that remains always to be articulated by the lights of tomorrow's best theories. All of this is to say that we might think about gleaning information about future physics by considering our current best physics in such a way that is different than how we glean information about the world by considering our current best physics. That being said, our current physics is of course not a perfect predictor of future physics. It not being a perfect predictor is good. It means we can think of the epistemic situation in the following way. There is partial information about future physics contained in our current theories. And based on that partial information, we can start betting about what will turn up in future physics. We can start betting, in other words, about the details of future physics based on our current best physics so far. But now these aren't bets about which features of our current theories will likely prove to last given our credences. That would require higher order trust in those particular credence values, which is part of the issue that I suppressed earlier in the standard presentation of dark sector research, where we're leveraging clues about the future theory in its own production. Instead, here, the bets I have in mind are bets about what work the future theory will have to do in virtue of its coming next. In particular, we are presently accustomed to thinking about our current theories in rather particular ways. Looking forward, we expect that the future theory will respect why it is that we have come presently to think about them this way. So beliefs about why our current theories are successful thereby warrant our committing to bets about the details of the future theory. Namely, on the basis of those details, we expect to recover our current understanding of our current theories. But these details can entail empirical problems within the context of that future theory. So provisionally, problems arise that would constitute barriers to our recognizing the future theory as adequate. So theorists get to be warranted to pursue solutions to those problems, consequent to their committing to the bets on the basis of current theory. In this way, the act of committing to those bets is tantamount to imposing new conditions of adequacy on the future theory. And the upshot is that we can regard those conditions of adequacy as brought about by our current best assessments of the world. This framework is, at least I claim, how we should understand the situation in dark sector research. Dark energy and cold dark matter are particular features of the future fundamental theory, about whose details we presently commit to bets. Some of these details are going to concern long-range effects of those features, as would be relevant to the study of the evolution of large-scale structure in cosmology. Some of the reasons to commit to those bets are going to concern our present understanding of the successes of lambda CDM within that same domain. And meanwhile, these bets are going to give rise to new problems for the future theory. So as a consequence of isolating the reasons for those bets in the first place, we form anticipations today about the future theory. Lambda CDM thereby provides a basis for our anticipating today the dark sector of future fundamental physics. And accordingly, dark sector research includes the activity of anticipating the dark sector, as well as any work spent problem solving on the basis of those anticipations. It may help here to be more concrete by way of a hypothetical. And in fact, I think this hypothetical is believed true in all of the examples of dark sector research I gave at the start. Our embrace of lambda CDM commits us, plausibly, to the descriptive accuracy of empirical claims about the evolution of large-scale cosmic structure that are made on its basis. But a host of these claims are not descriptively accurate by the lights of our current fundamental theories. This is because our current fundamental theories fail to provide long-range effects that lead to the correct predictions at large scales as are relevant when we're considering our present-day universe at large scales. Now, this means that there is, by hypothesis, a gap in our understanding of our present-day universe. In spite of what we take for granted about fundamental physics, we nonetheless continue to recognize lambda CDM as descriptively accurate. These gaps are telling. We seem compelled to bet that dark energy and cold dark matter ought to explain why we currently feel entitled to regard lambda CDM as descriptively accurate, in spite of our current fundamental physics. But then, so too, we presently understand our current fundamental theories to be descriptively accurate, in spite of facts about the evolution of large-scale cosmic structure. So whatever explanations we bet that dark energy and cold dark matter will supply in the first case, we anticipate that they will not preclude there being further explanations for the second. Now, the viability of those further explanations becomes a condition of adequacy on dark energy and cold dark matter as they appear within the development of the future theory. In other words, as a consequence of demanding that dark energy and cold dark matter inevitably accommodate the long-range effects missing within current fundamental physics, so too do we demand that the two quantities inevitably come to yield explanations as to how those effects were otherwise missed. The upshot of this alternative presentation is that we may understand dark sector research explicitly in terms of our leveraging current knowledge about the evolution of large-scale cosmic structure in the production and subsequent satisfaction of new conditions of adequacy on the future theory to be developed. Dark sector research is the arm of theory development in fundamental physics that is occupied with rendering as inevitable in the wake of future fundamental theory the recovery of cosmological commitments that stem from lambda CDM. So that's dark sector research. So I only have a little bit of time left, but I really did want to flag how I was talking about the gap between lambda CDM and current fundamental physics. At the very beginning, with a pretty picture up on the slide, I referred to lambda CDM as a cosmological theory that tells us about the evolution of large-scale cosmic structure. And this is essentially going to be me somewhat quickly clarifying what I mean by this, which I think is in contrast with how we often think about lambda CDM. So first, let me give the standard line. According to our current understanding of fundamental physics, gravity dominates other fundamental forces at long ranges. In the context of cosmology, this has been taken to motivate the following attitude. Since our descriptions of the world are only ever regarded as approximately true, bounded by the precision of our observations, an idealization gets to be warranted in cosmological practice. This idealization concerns our observable universe at the largest accessible scales in recent cosmic history, present day. Here's the idealization. At those large scales, any effects of the other fundamental forces in our present-day universe, besides gravity, may be presumed too small to be relevant to our descriptions. Whatever is our understanding of the evolution of large-scale cosmic structure within our present-day universe at the large scales, as it's going to be empirically constrained by observations of sky surveys and cosmic backgrounds. We can expect that evolution of large-scale cosmic structure to be well regarded in terms of an application of our current fundamental theory of gravity. In other words, our current fundamental theory of gravity, general relativity, provides a working theory of all that is possible with regards to large-scale cosmology. On this view, lambda CDM as our current concordance model of cosmology, the model of general relativity that accords with the cosmological data, it's understood to approximate our present-day universe as according to our current fundamental physics, but just when we focus on the largest scales. In other words, features noted in our understanding of the evolution of large-scale cosmic structure, according to lambda CDM on this view, they are assumed to admit a functional reduction to gravitational facts about fundamental physical degrees of freedom that comprise our universe, as according to current fundamental theory. And in particular, in this picture, dark energy and cold dark matter, they wind up as inferences about fundamental physics within our universe, above and beyond what fundamental physics we are already committed to. And these commitments stem from a demonstrated fit between lambda CDM and cosmological data. But cosmological practice seems to indicate that the success of lambda CDM is all but decoupled from its status as a concordance model built on our current theory of gravity as an approximation of our current understanding of fundamental physics applied to large scales. Instead, its success seems to be due to the brute fact that our present-day universe is, at the largest accessible scales, incredibly simple to model, at least as a relativistic system subject to a few working hypotheses, which give us approximately uniform space expanding over cosmic time. Now, this independence or decoupling is actually important for giving us a kind of evidence in favor of the attitude that motivated the original idealization. And so this decoupling is not an artifact of practice, but I think there from the start. Moreover, this situation is typical of certain theories in the physical and material sciences, which Bob Batterman has dubbed autonomous. As Batterman discusses, for any such autonomous theory, there are many ways that the world could fundamentally be such that the autonomous theory happens to be successful deployed in a certain context. Consequently, any fundamental descriptions of the world accorded to us by, for example, our current fundamental theories, these are going to fail to explain the success of the autonomous theory. When it's successful in a given context, its success is entirely due to the relevant system behaving in accordance with the theory's dictates. Now, a further story is then supplied about what it is about the system as considered across scales, which renders the system in accordance with the given theory when we take the perspective of just one scale. And so I've put up the reference to Massimi again, because I think this is one way to read her thesis about downscaling and upscaling problems, and especially in between scales problems in multi-scale modeling in cosmology. With this terminology in mind, the concordance model understanding of lambda CDM, I think essentially amounts to a stipulation that lambda CDM not be thought of as an autonomous theory. Its descriptions of the evolution of large-scale structure are correct only insofar as one imports dark energy and cold dark matter, which are regarded as gravitating degrees of freedom in fundamental physics. To the contrary, in the view of dark sector research told in terms of gaps in our current understanding, lambda CDM is an autonomous theory of the evolution of large-scale cosmic structure, that part of the world. Empirical claims about that evolution shape future fundamental theory via dark sector research, on the bet that future theory will accommodate the success of the autonomous theory that characterizes those particular empirical claims. And again, just to finish up, I put the paper by Massimi back up on the slide because I think the view I have is somewhat echoed there. cosmological practice, at least when understood as a practice of multi-scale modeling of our present-day universe, is not foremost an application of our current fundamental physics. Instead, it is foremost a practice of spelling out how various autonomous theories of the universe, when we consider the universe from different perspectives, how these mutually constrain each other. The shared spirit between my project and what I read in hers is that there's a measure of respect accorded to the theories of the target system, the universe, at each scale separately. So I'm past time, so I'll stop here. Thanks.
Thank you, Mike, for this really great talk. Let me remind you how we're going to be proceeding for the Q&A. Please, if you have a question, write your name in the Q&A box, and I'll promote you to the status of panelist, and you'll be able to talk with Mike directly. And Francesca, I'm going to promote you, and David as well. Okay, Francesca, please go ahead.
I'm connecting. So thank you, Mike. Thank you for this talk. I admit that I went through this talk being very often disturbed. Actually, in each slide, I had some comments, but then I realized that all the comments were boiling down to a specific criticism that I have. That is the fact that all the ideas that you have very clearly and very correctly developed, they are concerned not the community of theoretical physics, but they concern the community of particle physics, or in particular the community of string theory. So, I mean, I would go through each of your claims, and if you substitute theoretical physics, fundamental physics with string theory, I think I totally agree with you. But then I don't agree on the premises. I think that here you should be honest about the fact that you are selecting a particular group of a very narrow group of physicists, and you're looking at the kind of ideas that they are producing and the kind of methods and practice that they are putting in place. I mean, theoretical physics, it's composed by several communities that includes mathematical physics, statistical physics, condensed matter, and in particular the community of general relativity. In general relativity, there is no mystery about the cosmological constant. The cosmological constant is a part of the theory. So, I mean, and dark matter, especially in the relativity community, doesn't have to be necessarily be explained by new particles, so a new physics. In fact, I would say that today, the most pursued explanation for dark matter is just in terms of black holes. So, yeah, I mean, it was marvelous as long as you substitute string theory with theoretical physics.
So, thank you for the comment. Well, my first immediate response is to agree completely, in as much as string theorists themselves, historically and currently, are very happy to speak of a single theory that would span, say, all of the concerns of fundamental physics. And I suspect at the very least, that is what you were picking up on in my talk, where I am regularly talking singularly about future fundamental theory. And to that extent, I take your point that this is a much easier conversation to be had if I'm only engaged with that perspective on what is the practice of theoretical physics. I do want to push back slightly in the following way. When I talk about current fundamental theory, I mean something a bit more practice-based than maybe is suggested. And so likewise, I'm going to mean something a bit more practice-based by the future one. So the current one, I mean something like standard model particle physics plus local perturbative effects of gravity, with the promissory note that as you go out larger and larger scales, it's not merely the perturbative effects of gravity, but in fact the full regime of general relativity that becomes characteristic of what is true of fundamental physics considered only coarse-grained across sufficiently large scales. Now that's taken strictly a contradictory set of presumptions. And so I can't be referring to current fundamental theory as a single packaged item. But if I'm allowed to do that, and maybe I'm not allowed to do that, if I'm allowed to call that a current fundamental theory, then I think I can call a so plural inconsistent set in the future as likewise future fundamental theory. And so maybe that wins me back some mercy in your eyes.
Well, I don't think, I think that in order to, I like this final take of yours, but I think that then the reflection should shed light on what we mean by doing cosmology, what we mean by doing cosmology, by doing quantum cosmology in general, rather than try to immediately turn our sight to string theory or some specific practices in particle physics and so on.
I see. Yeah, I suspect you're right about that. I do mean to spend more time in the near future understanding what is the balancing act between taking cosmology on board to talk about fundamental physics and vice versa. Because I do think there's an interesting dual stance going on here. So thank you.
Would be happy, I don't want to take time from the others, but I would be happy to continue this conversation with you later on.
All right, thank you very much for this exchange. David, the floor is yours.
Thank you. Thanks, Mike, for something very thought-provoking. I mean, I was originally wanted to ask, very early in the talk, you started talking about lambda CDM as a fundamental theory, and I started to wonder what that meant. And you've addressed that to some extent in the comments at the end, but I've still got some sort of residual questions to clear up. So let me try this by analogy. I mean, if I take something like the electroweak theory, the GWS theory, so that's there's a sense in which when that theory was formulated, it was a fundamental theory in the sense that it was the best thing we had and the shorter scale thing we had. On the other hand, it never pretended to be a fundamental theory in the sense that it was explicitly phenomenological in various ways. It was very much a creature of the effective field theory era. It just underspecified what kind of things imposed high energy cutoffs, and at least depending how what you mean by it, it left underspecified the actual mechanism of spontaneous symmetry breaking. So it was phenomenological. It was also very well evidenced, it was state of the art of our level of evidence until the Higgs was discovered. So it feels like in particle physics, you can say two things about epistemologically about the electroweak theory. First, well, I guess maybe it's the same thing said twice. I mean, firstly, it's right, or very probably right. There's a very large amount of evidence for it, and that amount of evidence can be interpreted really pretty directly as evidence for that theory. Of course, it could turn out that we test the theory in a regime, or some regime where it makes claims, but where we haven't checked it yet, and those claims are false. But right at the moment, we've checked it in a bunch of places, and within the regime of spaces it's supposed to describe, it seems pretty damn good. So, firstly, we seem to have learned something from that. That's defeasible, but solid evidence of, in your terminology, an autonomous, or Bob's, an autonomous theory that's fairly robust against the details. But secondly, it's going to be a pretty hard constraint on subsequent physics. It was a constraint on any mechanism of spontaneous symmetry breaking. It continues to be a constraint on deeper physical theories that they reproduce the electroweak sector, and that they reproduce that electroweak theory. So if you'd asked me before this talk to say what do I think about lambda CDM and the empirical state, I would have said lambda CDM was pretty analogous to electroweak theory. In other words, we've got a lot of evidence, much less evidence, obviously, cosmology is hard, but a lot of evidence that lambda CDM is right. it models a bunch of stuff. It does all sorts of information details pretty well. I mean, obviously there's space to debate whether that's right. There are links to Siska's work, but at least putatively, there's a lot of empirical evidence for lambda CDM. So then it seems that one, it's a constraint on future theory that it reproduce lambda CDM in the sector that lambda CDM successfully describes, but also that we've got quite a lot of evidence that lambda CDM is correct. So, for instance, we've got quite a lot of evidence that there's a non-zero cosmological constant. We've got quite a lot of evidence that there's some kind of non-baryonic gravitating matter. We know at the phenomenological descriptive level, we know quite a lot about what that matter would have to be, even if that painfully under-constrains the sector. And as you say, it could be anything from light neutrinos to black holes. But in terms of its large-scale phenomenology, we know quite a lot about it. Now, it felt to me as if there were at least at several points that wasn't what you think the right story seems to be. That so perhaps I'll just stop blathering there and see. I mean, where's the place where you'd want to deviate from that account of lambda CDM?
So to put a pinpoint on that before I try to answer.
Yeah, good.
The account of lambda CDM that you're leaning on, for the sake of the question, at the very least, is one in which it is not merely successful as what we might call a phenomenological theory, but in fact is getting at what I was referring to as facts according to fundamental physics, just only considered at sufficiently large scales.
Okay. I wonder, I'm not entirely sure I understand the difference between those. I mean, does electroweak theory in that sense only describe the phenomenological, or does it describe facts about fundamental physics just at large scales?
Good. So this goes into that being your question clarified for me. So in the case of the electroweak theory, within fundamental physics, we aren't often talking, it sounds strange given the dominance of effective field theories making us attend to facts about scale. So this may sound strange. Mm-hmm. But we aren't actually used to thinking about, at least I think, systems at a scale, systems existing in themselves fundamentally at a scale where electroweak works, and then the same system, but now in an essential way considered at a different scale, it not working. But I think in the context of cosmology, we are often a lot more prepared to think about the full-throated large-scale universe as a different item under study than the full-throated universe considered at scales where fundamental physical degrees of freedom are relevant.
Okay. So that's helpful. We disagree in that case on quantum field, on particle physics. So that's perhaps and I don't want to derail the talk into discussion of ontology of particle physics. So I won't push the point, but that's the point of disagreement. Then it seems to me that in particle physics we are doing that much more so. But I could see that if you don't think that, then I can see much more the space for where the analogy you're talking about opens up.
I'd be hopeful. I mean, I'd be interested in talking about this further at another time. I'd be hopeful that the difference in the views sounds perverse given some of my other philosophical views, but I'm hoping that the difference comes down to branding. Perhaps with maybe some substantive differences at the end of the day with what it means to talk about a scale independent of, say, two different theories that are meant for two different things at two different scales.
Yeah. Okay. I mean, just as like a very quick coda as to what I have in mind. I mean, it would seem that something like saying, at a certain scale, this is a theory of protons, which are particles, and at another scale, there aren't any protons. The particles are quarks. That to me feels quite analogous to the the way in which in cosmology we move through scales. The ontological players are scale dependent in cosmology, but they're also scale dependent in particle physics.
I see.
But let me not abuse my time any further than that. Thank you.
Thank you.
Thanks, David. Siska, floor is yours.
Hi, thank you. Thanks, Mike. This was super interesting. I think my question is sort of actually following up on David's in a way, in the sense that I was also wondering about this multi-scale modeling questions and like the autonomy of theories on different scales. And I guess what I'm curious about, and this goes back to some previous conversations we've had, is the effects of dark energy and the effects of cold dark matter are ostensibly visible on different sets of scales, right? And so I was wondering whether you could say something about how you think the fact that like dark matter is supposed to be effective on galactic clusters and cosmological scales versus dark energy ostensibly mostly having an effect on the largest scales, how that affects the future theorizing on both of these like dark sector components, if that makes sense.
So first up would be laying cards on the table of it might sound by me talking about sort of respecting autonomous theories that become relevant at different scales. It might sound like I'm relying heavily on there being scales as something we can appeal to as a concept independent of our practice of multi-scale modeling out there in the world. So we're literally dealing with coarse-grained descriptions rather than fine-grained descriptions, where it's some sort of spatiotemporal unit that we're coarse-graining with respect to. I don't want to grab on board to that view. In fact, when I want to accord a measure of respect to the theories that happen to be successful as autonomous theories at a scale, I want to treat that as a coupled unit where I'm learning just as much about what it means to consider the system at the scale as I am learning that the theory is successful when applied to the system from the relevant perspective, namely the large scale. So just to isolate one way of talking about the difference between cold dark matter and dark energy, which I don't want to get into, would be, oh, in one case we have different scale access to the same thing, in the other we only have one scale access. All that being said, I'm quite interested in all of the theoretical activity that gets pumped into the relationship between dark energy and fundamental physics research, because it's so clear that the only access to it is this coupled large-scale universe and some desiderata in our theorizing about fundamental physics. I do admit that the narrative or the discussion becomes a lot more woolly with cold dark matter. And this is where I think Michaela Massimi's paper is probably more insightful than I could be in regards to this. Once you have multi-scale considerations, when you think you are talking about the same subject matter across scales, it might just be a sufficiently different beast in how we're using it in our theorizing. I'm most interested, so in her framework, she talks about the in-between scales problem, where the biggest problem, once you think you're talking about the same thing across scales, is we can always theorize about that thing that exists across scales and get a multi-scale phenomenologically accurate picture. But the difficulty there is what is left as an independent empirical test of the theory that we develop. And because of that sort of epistemological problem, I'm prepared to concede that there may be a separate beast going on there. Does that help. It was somewhat rambly, but you're used to my rambles. So.
Siska, you want to follow up or?
That's fine, thank you.
That's fine. Okay, good. Thanks, Siska. We don't have anyone in the queue at this point. Let me just take a few minutes to invite if any of the attendees, if you want to ask a question to Mike, please take the opportunity now and write your name. Okay, let me just wait a minute. Nora, I'm going to be promoting you. All right. Nora, the floor is yours.
Hi, Mike. Thanks for the great talk. I think I have a fairly kind of low-hanging clarification question, and I'd really love to see this paper or whatever you have written of it so that I can look at it in a little bit more detail. But my question is, so in your talk you emphasized this distinction between the empirical constraints on a future theory and the empirical constraints on theoretical development itself, right? And at some point you mentioned that one might be tempted to deflate these things, and at that moment I was like, yes, I am. I'm that person. And then you signaled that you had some other arguments for not wanting to deflate them. I wondered if I could push you on that a little bit, and let me say just a couple more things about what I have in mind. So, I'm not. I guess I'm having a hard time seeing exactly what the sense in which you could have empirical constraints on current theoretical development or future theoretical development that wouldn't just amount to the regular kind of empirical constraints. So like, I'm happy to say that, enriched evidence empirically constrains future theorizing, in that any future theorizing would have to be consistent with the growing body, with the growing evidential corpus, right? And like, in that sense, we need to recover the successes and failures of our current theories. But I take it that you want something more than that for this sort of second type of empirical constraint on theoretical development itself. And then I started thinking about, Richard David's type arguments where, we have these sort of meta-empirical constraints. And I wondered if that was sort of what you thought about his views, and if yours was sort of a flavor of that sort of reasoning, or maybe you can just kind of clarify for me once again why the constraints on theorizing itself don't collapse to just plain old empirical constraints on any theory.
So let me give. I worry that these don't, in fact, amount to arguments so much as intuition pumps, but I hope they're arguments. So the first big one is part of my project in a sufficiently abstract sense is me trying to get a grip on the further subject of dispute that I think one sees in Sabine Hassenfelder's criticisms against beauty considerations, or Carlo Rovelli arguing that we need to proceed by continuity in our theorizing. We can't just sort of sample idea space. So I take there to be a further point of contention where charitably all parties agree that the world should push back, and it will push back once we have a theory that's sufficiently prepared to ask how it survives against our accumulated evidential record. The further point of disagreement is, what role do explicit empirical considerations have in the developmental process where we're preparing our theories to try to survive that test? And so insofar as there's a further point of contention, I would hope that there's two different notions. So I say I'm concerned that that's an intuition pump rather than an argument, because it might be that the resolution to that further debate shakes out to be that one side is just confused, namely, if they're going to be full-throated empirical about it, they ought to be incorporating it. So that would be why that isn't a full argument for it. The other one, because you mentioned David's work, I'm actually pretty worried about stylized decision paradoxes or decision problems that come from like acting based on beliefs about future end products of my action. And so another reason, again, not sure if it's a full argument rather than just a intuition pump, another reason to want there to be two notions at work here is I want to possibly avoid those hairy situations. And this is something that I think plausibly one could apply pressure to how David sets his framework up. Namely, we're looking for confidence that the future theory will be stringy as justification for my continued pursuit of the future theory by means of a string theory toolkit. And so one way of categorically avoiding all of that is to get on board with there being a second notion whereby you can use empirical appeals, you can use theory-related empirical claims directly in the process of theory development as a matter separate from the sorts of claims that you expect to be the test of the theory so developed. Does that help at all?
Yeah, I would have thought that there's sort of pragmatic or aesthetic constraints that you can have on the development of theories or theory pursuit. And I want to be very liberal about those, like, you can have whatever kind of favorite reasons you want for pursuing a theory. And the sort of the rubber meets the road with the empirical constraints. And I'm still not quite seeing how you can, I understand that without the future theory, we aren't yet in a position to make the evidence well adapted, the empirical results now well adapted to that future theory. But I still don't quite see how there's more empirical constraints there than just the normal kind. But I probably have to read your paper. So.
I mean, I'll say one more small thing to maybe help with that. So in what I take your lingering surviving worry to be, in what sense is the use of theory-related empirical claims in theory development, as I've set it up, an empirical constraint on the process and not just one of the helping hands that we might appeal to do our jobs as theoreticians? Is that the?
Or it's like, if they're empirical, I don't see how they're not just the empirical constraint. Like, if you have evidence in the way that I conceive of it, where it can kind of make these transitions across boundaries of theory change, then insofar as what's doing the constraining is that evidence, then it's just the regular empirical constraint. But if you're not talking about empirical constraints, then of course there are plenty of other things that guide theory development. They're just not empirical. But that's because people, like to pursue different kinds of theories, and that's totally fine. But that doesn't have the sort of epistemic, significance of the empirical constraints.
Yeah. So this is helpful pushback, because I do think I have a way of responding, and it does depend on the anticipation stuff that I'm building on. But I might need a clearer way of making it into a slogan. The smallest the smallest bit I can give here would be, I really do want to take seriously the idea that once we've made certain demands in the course of our theorizing, we've inherited or spontaneously generated new full-throated empirical problems. But this is well before we've fully, or even partially in some cases, fleshed out the theory to say it's an empirical problem for the eventual future theory that would be at the end course of that development. And so the context is going to be a different context than the future theory, and nor is it the context that existed prior to the sort of start of that activity with the current theory. It's sort of an intermediary.
All right, I think we are going to leave it at that since we're reaching 1:30 as usual. Thanks, Mike, for this great talk, and thanks for the audience for the Q&A. We will not see you on Tuesday. Go and vote rather, and we'll see you on Thursday for the community ontology seminar, and on Friday next week for the annual lecture series with Liz Westerlund. And the next lunchtime talk will be in 10 days from now, in a week and a half from now. Thanks, Mike, again. Been a real pleasure. And have a great weekend all.